In the today's class, we will study the effectiveness NTU relation for counterflow heat exchanger. So already in the previous classes we have written this equation for counterflow heat exchanger: log of TH2 minus TC1 divided by TH1 minus TC2. This will be equals to minus U into A 1 divided by MH into CPH minus 1 divided by MC into CPC. So already we know that MH into CPH is given by CH. So let me write here, this equation I have written as it is, minus U into A, whereas 1 divided by MH into CPH is given by CH minus 1 divided by MC into CPC is given by CC, where CH is the capacity rate of hot fluid, where CC is the capacity rate of the cold fluid. Now, assuming CH as C minimum and C of C is equals to C maximum, I can assume any one of the fluid. I can assume this C of C as the C minimum and C of H as the C maximum. In this condition, CH is less than CC. So whichever the value is lesser, we are going to consider that as the minimum value. So now here let me write log of TH2 minus TC1 divided by TH1 minus TC2. So I will take here minus U into A. I will take 1 divided by CH as common. If I take that as common, where CH is C minimum, directly I will write here C minimum. So in the bracket 1 minus, so this will be C1 minus, if I will take 1 minus CH as common, then this will be CH divided by CC. Then directly I will write here 1 minus C minimum divided by, or we will write here C minimum divided by C maximum. So I have taken CH, 1 divided by CH as common. So this will be 1 divided by CH. 1 divided by CH is replaced by C minimum minus CH divided by CC. C minimum divided by C maximum. So this equation I will write TH2 minus TC1 divided by TH1 minus TC2 exponential of, so UA divided by C minimum, it is given by NTU, where NTU, number of transfer units, is given by UA divided by C minimum, 1 minus C minimum divided by C maximum. I can write it as C, whereas capacity ratio C is equals to C minimum divided by C maximum. So already in the previous class we have written the values of TH2 and TC2 values from the effectiveness of the heat exchanger formula, whereas this TH2 value is given by TH1 minus epsilon into C minimum, the bracket TH1 minus TC1 divided by C of H, and TC2 value is given epsilon of C minimum, the bracket TH1 minus TC1 divided by C of C minus TC1. So these values we have already calculated in the previous derivation, that is parallel flow heat exchanger, from the formula effectiveness of the heat exchanger. Already calculated these two values in the previous class. How we have got these values TH2 and TC2. So here directly I have written the values because in the last class already we have derived it. So these values TH2 and TC2, both these values I will substitute in this equation. I will call this equation as equation 1. I will substitute both these TH2 and TC2 values in this equation. So let me write the values. So TH2 is given by TH1 minus epsilon into, already I have assumed CH also has a C minimum. So C minimum gets cancels. So my final expression will be TH1 minus TC1 minus of TC1 divided by, now I will put this value TH1 as it is minus TC2, where TC2 is given by epsilon into C minimum divided by CC is C maximum. So C minimum divided by C maximum is C, that is capacity ratio, TH1 minus TC1. So minus TC1, this will be equals to exponential of minus NTU in the bracket 1 minus C. So here also TH1 minus TC1, here also in the denominator also it is TH1 minus TC1. So in the numerator side TH1 minus, the numerator here it is TH1 minus epsilon into TH1 minus TC1 minus TC1. So TH1 minus TC1 I will take it as a common, 1 minus epsilon. So in the denominator side this will be, in here TH1 minus TC1 as common, 1 minus epsilon into C. This will be equals to exponential of this minus NTU, I will write minus N is nothing but NTU only, 1 minus C. So here also TH1 minus TC1 minus TC1 gets cancels. So my final expression will be 1 minus epsilon divided by 1 minus epsilon into C. Epsilon is nothing but here, this is the effectiveness of the heat exchanger. This will be equals to exponential of minus N in the bracket 1 minus C. So now I want to write the expression in the form of effectiveness. So I will make the cross multiplication. So 1 minus epsilon, this will be equals to 1 minus epsilon into C into exponential of minus N bracket 1 minus C. So 1 minus epsilon I will keep as it is. So 1 into this term. So this will be exponential of minus N in the bracket 1 minus C minus EC into exponential of minus N 1 minus C. So already I have written here this term into this term, 1 into this term. So equation remains as it is, minus this term into this whole term, minus epsilon into C exponential of minus N in the bracket 1 minus C. So one minus 1, I will take this term to this side, 1 minus exponential of minus N 1 minus C. I will shift this term to right side. So epsilon minus epsilon into C exponential of minus N the bracket 1 minus C. So I will write the same term, 1 minus exponential of minus N 1 minus C. The equation as it is I have written. Here also epsilon here also epsilon is there. I will take epsilon as the common. So 1 minus C. I will write this in the entire bracket. 1 minus C. Epsilon I have taken common. So this will be exponential of minus n in the bracket 1 minus C. So now already effectiveness term is separate. So therefore effectiveness, this will be equals to 1 minus exponential of minus n, the bracket 1 minus C, we'll write it in the square bracket, divided by 1 minus C, the square bracket I will write, exponential of minus n in the bracket 1 minus C. So this is my final expression for the effectiveness of the heat exchanger for the counterflow heat exchanger. So now if I will assume now CH as C maximum and C of C as C minimum, that means here CC is greater than CH, this condition. Here also we are going to get the expression for the effectiveness of heat exchanger in this form only, 1 minus exponential of minus n in the bracket 1 minus C divided by 1 minus C into exponential of square bracket I will write minus n 1 minus C. So this is my final expression for the counterflow heat exchanger, that is effectiveness of counterflow heat exchanger. Even though I have assumed CH as the C maximum and CC as the C minimum, here also we are going to get the final expression in this form only. So now here also we'll study some two different cases for special cases. So we are going to get some two special cases, how we have written it for the parallel flow heat exchanger. So for condenser or a boiler, if the problem is based on a condenser or boiler, that is any one of the fluid is going to change its phase here. So here effectiveness is given by 1 minus exponential of minus NTU, where NTU you can write or just you can write minus N. And in the second case, when C is equals to 1, that means C minimum will be equals to C maximum, that is CH will be equals to CC. That means when both the values CH value and CC values are same, then we are going to get C is equals to 1, that is C is nothing but C minimum divided by C maximum, and C is equals to 1 means that is when both the values CH value and CC values are same, then we are going to get C is equals to 1. When C is equals to 1, this effectiveness of the counterflow heat exchanger is given by NTU, that is N divided by 1 plus N, NTU. So this is my final expression for the condenser or the boiler effectiveness for the counterflow heat exchanger, and the effectiveness for the counterflow heat exchanger when C is equals to 1, or we can write this equation epsilon is equals to N divided by 1 plus N, both are same. So this is the effectiveness of the counterflow heat exchanger.